Okay, today we're happy to have Itay Bloch from Berkeley telling us about Axion dark matter profiles.
So thanks for having me again. So just to make sure we're on the same page, we're going to talk about dark matter. So just to remind you, we have Ruben and Ford and others looking at their telescopes, seeing some weird stuff. Here's a slightly more usual way to see it. So basically, they're looking at the velocity, function of distance for a bunch of galaxies. And the thing is, when they measure the contributions from stars just using Newtonian gravity, you can kind of show that that's not enough to explain the velocity we are seeing. You can add the gas, that's the fancy thing that they did, okay, that's the major contribution there. But really, we are missing a lot of mass, and this is kind of what we talk about when we talk about dark matter. So, in the broadest of strokes, basically dark matter is meant to explain a bunch of different observations, right, that basically we see gravity acting around nothing, so we just add non-shining dark matter, and it seems to work quite nicely. Now, we don't know a lot about them, but we do know they're not a part of the standard model, okay? You're not going to find them in a periodic table, or you know, just regular old particles we know and love. And we also know roughly the energy density, so around 85% of the matter is dark matter. And we also know that it's cold, that means it has been moving at non-relativistic velocities for billions of years, and usually we kind of know all of these, but of course we also need to remember that we do know that it cannot have very strong interactions with us, so if we really want to measure it, we have to be smart, and usually my approach is to try to come up with smart measurement methods, but today we're going to talk about how actually understanding dark matter better might imply that it is easier to measure maybe than we thought it would be, or harder depending on your kinds of searching methods. So this is kind of most of what we know about dark matter, and there's a lot of uncertainty, as you can guess, when this is basically all that you know. And one big question mark is the mass of dark matter. And today we're going to talk about ultralight dark matter, which is an interesting possibility. So we can write down the number density. It's just the energy density divided by the mass. And you can do a simple calculation where you estimate the distance between two particles from this density. And at some point, it becomes dense enough that the distance between two particles is actually less than their size, their Broglie wavelength. Right? So they are no longer like point-like particle here, point-like particle there, because they overlap on top of each other. And this is the ultralight regime. Different people define the ultralight regime at different places, but it doesn't really matter. Basically, the point is we are going to treat these particles as some classical wave. Okay? So, just like light from a lamp, usually you don't need to think photon by photon, right? The dark matter particles are basically acting in this coherent manner. We can think of them as some kind of plane wave. And because they are not relativistic, very often we just ignore their momenta. So the dark matter particles oscillate at a frequency which corresponds to their mass. But as you will see, this talk is one of the places where actually the assumption is the wrong one to make. Even though they are not relativistic, ignoring their momentum is going to be really bad. So, arguably, the most interesting ultralight candidate, but I think inarguably the most popular one, is the QCD Axion. So what the QCD Axion is meant to solve this problem known as the strong CP problem. It's not super crucial for us what exactly the problem is. There's this parameter, theta QCD, that we have not yet measured. Basically, the Axion can mimic its effects, and is getting a potential which is minimized when it cancels out every effect of this parameter. Okay, so the Axion is basically meant to hide the effects of this parameter. Now, it can be a component of dark matter, okay, and in this talk I'm going to be assuming that it is all of it. You can easily kind of scale all my arguments. The standard method of making axions in the early universe is you have some potential, the same one we just wrote earlier, and in the very early universe you get stuck at some point along this potential because Hubble, the expansion of the universe, is kind of like friction, okay, so like you just get stuck here. However, our expansion of the universe, Hubble has been becoming smaller and smaller. So the axions are only getting a mass at some point, but that's not super crucial for us. But basically, at some point, you are released from this potential, you start oscillating, and that is essentially dark matter. The oscillation of this field is just what we think of as Axion dark matter. Now, there are some variations of this, not super important for us, the exact details of the production. What is important is to understand what kinds of interactions do we have. So the axions are pseudoscalars, okay? And usually they have derivative couplings. Okay, so d mu A is the Axion field, and it couples to some fermion current. Okay, there are some exceptions, and we're going to talk about one of them very soon. But basically, they can mediate new long-range forces between two fermions. You can have a particle that's going to radiate these axions, and if you have some background field value, then there's going to be a potential induced on fermions, and you can try to look for that potential. These are kind of, I think, the three primary ways we can try to look for these particles. But the one last thing we need to know about the QCD axion is that their mass is inversely proportional to their coupling constants, basically. Or sorry, is proportional to their coupling constants. So basically, if we're talking about lighter and lighter QCD axions, they are going to couple less and less to the standard model. Okay? And that's very bad for us because we want to talk about stuff that's very light, but this will also mean that it couples very, very weakly to the standard model. So actually, we're going to focus on axion-like particles. They are very similar to QCD axions, but not necessarily related to the strong CP problem. A lot of theories admit them. Basically, if you have some symmetry and you have a soft breaking of it, you would get a very small mass. Okay, so it's not that hard to imagine. A lot of theories can produce them. They can still be dark matter, still have similar couplings, but now the mass and the coupling constants can be almost decoupled, and that's why it's a lot of a broader part of the parameter space that you can try to look for. Now, there are three primary ways we look for axion-like particles, or axions in general. They're coupling to photons. That's something I mostly do with the Snipen collaboration. And as John has written in his paper, maybe that's also not as simple as we necessarily think usually. But this is kind of the three main ways. The coupling to gluons. Now this is a bit of an exception to the statement I made earlier, which is derivative couplings. This breaks the shift symmetry because GG dual is a funny little thing. And the last thing, which is kind of what I usually do, is the coupling between axions and fermions. So this is spin-based experiments can look for this. But today we're actually going to talk about this one, which is not exactly shift invariant, but only kind of talk about this one. And the reason why I say this is that you're not actually going to see gluons here, because, gluons are not really a thing you see around you, right? Like, where are they? Well, they're inside matter, right? Like, they are what makes a proton. So we need to understand what this looks like using the degrees of freedom that are actually around us in our low energy, universe. And basically, one important contribution for us is the fact that the potential I mentioned earlier is actually related to an interactions of the axions with pions. Okay, so the details are not super important about what exactly this term is. Okay, this is from this term we essentially get this term, which is the interactions of these axions with the pi zeros, and because quark masses are changing when you have a high density object, okay? Essentially this means that when we are inside a different density object, this potential is going to look different, okay? So the axion potential is modified by the presence of matter density. And what this means is that really the axions are actually coupling to matter density. And from the quantum numbers, okay, the numbers here don't really matter. The important part is that we have some nucleon bar nucleon, okay, so n bar n, coupling to a squared, okay? And this is the coupling we're actually going to talk about today, so you can either think of it as arising from this GG dual, but actually I'm never going to look at the gluon part, so all I really care about is that I have some particle with these kinds of couplings. Now, through a loop, this coupling actually creates a correction to the axion mass, okay? Because this is an a squared term, a squared is basically a mass, you can kind of get a loop of fermions, okay? So what this means is that usually we can just say that axion-like particles, the mass, the coupling constants are unrelated. Here, that's a bit of an iffy statement, okay? It's a bit less trivial because essentially if you just write down the more basic model, this would mean that you are fine-tuned. Now, there are some models that go around this, okay, but I did want to kind of emphasize that this is a bit of a weakness of trying to treat these as independent, that there are these non-trivial models that can actually give you this if you try to write down the full theory. Yeah?
So, are we still talking about something that works both the same for QCD axion and Axion-like particle, or now this is something you have to go to Axion-like particle?
So basically, if you wanted to just have the standard QCD axion, you would not be able to disassociate. So this Fa, okay, would immediately tell you the mass of the axion, okay? So if you now wrote a generic axion-like particle and you wrote this interaction, that is actually still true. However, there are models where basically this interaction, despite seeming to create a mass correction, doesn't actually, or basically there are other terms that cancel it out. The one I know is like the ZN model of Ans and Hoof. And basically, the statement is that this is, in essence, an axion-like particle, but it actually can still solve the strong CP problem. Because, again, in that at least one implementation, you still are able to solve the strong CP problem. Okay? But there's a lot less freedom compared to usual, where you can say, oh, this is a generic outcome of a bunch of string theories or whatever makes you happy theories. Okay? Here, there are a lot less models that would actually give you a large coupling this coupling to be large, while still having a very small mass. Right. But the interesting part for us, so this is kind of, I didn't want to hide this from you, but the interesting part, the thing that we're actually going to talk about, is the fact that, again, n bar n, and that's like the nucleons, right? So neutrons and protons is the the doublet of isospin, basically, NP. If you have matter density, n bar n is basically rho n, the density of matter, divided by the mass of the nucleon, okay? Roughly speaking. And this means that really axions are going to get a contribution to their mass, right? A squared is how we write masses in Lagrangians. So their mass is going to be different inside and outside the Earth, okay? So this is kind of the thing we're going to talk about. So again, we're going to talk about wave-like axion dark matter, okay? So ultralight axion dark matter, and in particular, we're going to talk about the coupling, which makes the mass of the axion different inside and outside the Earth. Now, I'm going to set up the problem in just a second. Then I'll show you kind of the main results of this whole story. So if you come out remembering one thing, it should be, if you ever want to remember what I'm talking about, you should open the paper, look at this plot, and read the caption, because this is going to summarize basically all of the rest of the talk. Then I'll tell you a bit more details about, some of how we get to this, the description of all the different aspects of the problem, of the different parts of the parameter space. I'll tell you a bit about the experimental implications. How does this actually affect experiments looking for these particles? And I think another important part is really kind of the future of how I see continuing this forward, because I think this is kind of a step forward, but it really is not the final step in this direction. So, let's set up the problem. Why should I care about this coupling? Basically, I get a correction to the mass squared, which is roughly speaking 10 to the minus 2 times the density of matter divided by this Fa squared. It's just the coupling constant, or the decay constant, if you write Fa. And I will start with a toy model, and I will basically show you that even this toy model is actually extremely rich in phenomenology and extremely complicated. So before we try to actually solve the full history of the Earth, let's try simplifying things. So, sphere of radius r, density rho, seems like a very easy thing. What is the equation of motion I have? Well, basically, outside it's just the Klein-Gordon equation, so box plus ma squared of a is equal to 0. Inside I have some ball of radius r, and I'm just modifying the mass squared, okay? So it's a step function for the mass outside and inside. I also need some boundary conditions at infinity, okay, to say what this field looks like in infinity. And I also need some initial conditions, though I'm basically going to ignore this in the talk and assume that there's some steady state solution, okay? So like, I'm going to just assume self-similarity, I guess it's called, whatever. I'm just going to assume that there's some stability here, so no dependence on the initial condition. Okay, so this is kind of the basic setup. Now, what is new about this? Well, I'm not the first person to talk about this mass-induced changes for scalars. In fact, we even have Marcus here, who has spoken about what this does. So what is new? Well, the usual thing people talk about, which is also in particular the difference between this work, Marcus and Ken's work, is that we usually take the mass to increase inside the Earth. And the reason is that this kind of can suppress a lot of the effects, okay? So the particles are harder to look for, it can evade more constraints, maybe stuff like this. For the axions, it turns out that generically, actually the mass is decreased inside the Earth. It's just, I don't know that there's a fundamental reason to this. It's just a matter of like, if you write down the chiral perturbation theory Lagrangian, turns out the sign is a minus sign. At least as far as I know and the rest of the authors, right? There might be a deeper reason, but it's like 50-50, so we don't necessarily need to break our heads. Now, the other thing that is new here, so usually when people do discuss the mass decreasing, they focus on the case where the change in the mass is actually, the change in the mass squared is bigger than the mass squared. Why is this interesting? Well, this would mean that inside the Earth, there's a negative mass squared for the axion. So you'd get essentially a tachyon mode. Okay, so the axion wants to fall to minus infinity. That's the regime that, as you will see, I will just have a red region for. Like, I'm not computing anything there. Okay, it's a bit more subtle than just this condition, but basically, once this thing happens, plus one other constraint, it's just our EFT of just treating this term breaks down. There's a runaway direction in the potential, and you can't really calculate anything. Okay, so we're going to focus on the other regime. And as we will see, there's a lot of interesting stuff to do there. Now, it's not true that no one has really talked about this. There's one group in particular, which was a recent paper by Bauer et al. Last year, but they ignored the Axion momentum. And as you can guess from the title, I'm going to try to convince you that Axion momentum is important. I'm not going to try. I'm going to succeed. If you will listen, you will be convinced that Axion momentum is important because it is crucial to the calculation and it changes the whole story. So, what are the equations of motion? So again, I now just do a Fourier transform. So, same thing, except now I wrote explicitly omega squared. I have some Nabla squared and the mass squared. I have the Earth, 6,400 kilometers-ish. And the mass inside is different. And if you just plug in the density for the Earth, this is roughly the change in the mass squared. Okay, so it's important to remember, it's not actually m goes to m plus minus delta m. It's actually m squared minus delta m squared. Okay? And at infinity, I'm just going to assume the field is some plane wave, is some momentum Ka. Now, what was done by the Bauer group? Well, they just solved this equation by taking Ka to 0, just ignoring momentum completely. This seems reasonable, and we often do this, because they are not relativistic. So why should I care about momentum when most of the energy in the particle is actually sitting in its mass? Well, this is like the title, literally I think the title of our paper. Momentum does matter for Axion dark matter, matters on Earth. Okay, we will see that this is not a good assumption. Why? Well, if I do take their approach, I just assume that at infinity this is e to the IMAT. Inside, this is the equation of motion. Now it's spherically symmetric. All the boundary conditions are spherically symmetric. All of the equations are spherically symmetric. So I can just take the Axion field to be spherically symmetric. This is the equation outside. And I will just spoil the ending. This is the actual solution. So you get some constant plus 1 over r at outside the Earth. And this is, again, multiplied by e to the IMT. And inside the Earth, you get the sinc function divided by cosine of delta m r. So this was kind of their solution. And when we look at this, we should be very worried. And the reason we should be very worried, and also their title is kind of worrisome, is that whenever delta mr hits pi over 2 plus pi n, this thing diverges, right? So this would mean that our description of Axion dark matter is actually completely broken, okay? It doesn't make any sense once you hit this delta mr to be pi over 2 plus pi n. And for a lot of Axion's experiments, we are at the regime where delta mr is actually a very, very big number. So who knows whether it's pi over 2 plus pi n or not, right? So this would mean that we should not actually forget about this effect of the a squared. Now, however, again, as I mentioned before, this does miss the importance of the Axion momentum. You can see that there is no dependence here on the mass of the Axion, and the reason for that is actually because we forgot about momentum. So this is actually, what we usually call the Axion energy, and that is not going to change. We have elastic scattering, so inside, outside, the momentum is not going to change. But we can define an effective momentum inside the Earth, okay? And it's just going to be enforced by having the same amount of energy, but now I have a different mass, right? So basically the mass inside the Earth is going to be just this thing, okay? The square root of delta m squared plus the k of outside squared, okay? And here we can see that basically, if we just compare the momentum to the mass, we're not actually doing all of our jobs. Because here, okay, this thing, if k is very close to, is much bigger than delta m, then actually, both inside and outside, the momentum actually is not going to change. So the effects of the mass are actually suppressed if I have a large enough momentum, okay? And this is why there's more than just comparing k to v and delta m to r that are actually important for us. Okay? So this is kind of why we would imagine that it's important. Now, if you wanted to write down the actual full solution, it's a bit complicated. So we have a spherically symmetric equation of motion. Our boundary conditions have azimuthal symmetry, right? Because it's just e to the ikz. Okay? So you can do some multiple expansion, ignore the m modes because it's cylindrically symmetric in terms of boundary conditions. Okay? And now we just need to solve what are these RL, these functions in the R space. And, you know, the theta here is just like, if you're measuring here and the axial momentum is over there, it's the angle between where you are standing with respect to the center of the Earth and the original location of the axiom. Right? So we now need to solve for these individual multiples. Okay? So we have actually a much more complicated solution than the spherical symmetric one that we had before. Now, inside the Earth, okay, I'm just going to tell you what these solutions look like. It's not really super important in the details. Basically, these are spherical Bessel functions, okay, with some coefficients. They look like sine of the momentum times r, okay, which is roughly what you would expect, right? If you have some momentum, sine of kx is the standard solutions. But there's this polynomial in 1 over r because we're doing this multiple expansion, and there's also a cosine term. And the important detail is that, you know, their choice here of the coefficients are such that there's no divergence at the center of the Earth, right? Because there are polynomials in 1 over r, so as you might expect, if you're not choosing the right polynomials, they would diverge. Now, outside, it's a bit more complicated. So if we remove the scattered wave, so if we remove the original wave, it's still kind of Bessel functions, but this time there's Bessel function of the first kind and the second kind, which are actually, you know, can be written as Hankel functions. Whatever, it's not super crucial for us, but it does kind of look like e to the minus ikr, so that's, you know, a wave that's like leaving the Earth. If you take e to the minus ikr plus I omega t, that looks like something that's like moving away from the Earth, okay? Assuming I said the sign correctly right now, but, you know, it's either plus or minus here, it doesn't really matter. The point is that, you know, we have these solutions that are not necessarily super complicated in terms of the actual form, right? I can write this down, and we're done. But actually, these coefficients are quite ugly, and these functions are actually quite complicated, and they can lead to very non-trivial effects, which are not actually fully resolvable in terms of like numeric stabilities. Importantly, however, there is no more any divergence. So before we literally had a divergence wherever delta mr was equal to pi over 2 plus pi n, that was just the equations blow up. Here, as long as the momentum is non-zero, we can just show, we did it, we had like a full proof, we like for all epsilon bigger than 0, blah, blah, blah. We had like some, which was a series that we show is convergent. There are no more any divergences. And in fact, even the stuff that's going on at k equals 0, if you assume that the axial momenta are kind of distributed along some kind of finite range of momenta, there's only an infinitesimal amount sitting at actually k equals 0, and that infinitesimal amount is enough to cancel out the divergence. So like the d3k times whatever observables you want to look at are actually going to converge. Okay, so that's nice that, you know, at least it tells us that this toy model will not have divergences, so maybe it is somewhat reasonable. Okay, compared to previously, where it was just like, oh, we don't know what to do once we see divergences. Okay. So, again, the point is, even for a spherical Earth, the coupling of axiom to matter density can lead to pretty non-trivial equations and pretty interesting effects. And due to the axiom momentum, you know, solving these equations is highly non-trivial. If you just ignore the momentum, you get an answer, but it's very misleading. But once you add the momentum, there's some non-trivial stuff. And now I'm going to kind of try to tell you all the interesting parts about the final answer, okay? And as you will see, there are a lot of different moving parts here. But this is, I would say, the main takeaway message is this part and the future directions. So, we're going to plot 1 over Fa, right? Fa was, again, the thing characterizing how strong they couple. So, the smaller this is, the weaker the coupling, as a function of Ma, okay? The first thing I want to add is some dashed line. Now, this dashed line is not, you know, it's kind of just to help you place yourself in this 2D parameter space. Basically, above this line, you would expect the largest effect. This was what Bauer wrote as like where the theory breaks down. But as we will see, it doesn't really break down. But at least naively, this is when you start having these delta mr equals pi over 2 plus pi n. So maybe you would expect to see large effects because the Earth start acting importantly. Now, the other line I want to add is something that you wouldn't necessarily have guessed in advance, okay, but is quite important, which is when the momentum of the axion times the radius of the Earth is order 1. Why do I care about this? Well, let's say I take the momentum of the Earth, the momentum of the axion to be arbitrarily small, but I do take the interactions to be very strong. What this means is that the axions are going to get features at the order of, right, the radius of the Earth. So the radius of the Earth is a new spatial scale, which means if I look at Fourier transforms, it's a new momentum scale. So to the left of this thing, okay, I would expect kind of to start seeing some bigger effects in terms of like the derivative of the axion field. Okay, it's going to modify things in terms of derivatives because it's introducing a new typical scale to the problem. Again, this is a rough way to view this scale. The first thing I want to add is basically when do we see that the axion field value at the radius of the Earth is strongly affected? Okay, this is kind of the first question you would be interested in asking. And the answer is roughly in this blue region. Now, what is this line? Well, this line is basically when the momentum is comparable to the change in mass. So it's exactly when you really cannot actually ignore, this delta m compared to k. Okay, so the Martin-Bauer, because they ignored the momentum, it was actually just everything above this delta m r equals 1. But here we're saying actually, as soon as the momentum is bigger than delta m, it's not really important that the Earth is here, because already, you already have enough kinetic energy to not worry about the small change in the potential energy. Okay? And quite generically, we see that the field value is actually suppressed. So if you're an experiment looking for axions and you're sitting here, you would expect your sensitivity to actually go down. Now, there is a subtlety here that we're going to talk about later, but generically, it seems like this is what the numerics tell us. Now, the other region here is the region where the gradient is enhanced. It turns out this region does not fully overlap with this region, okay? And indeed, the fact is that because of this new momentum scale, you get this kind of enhanced effect, even though the axion field value actually isn't modified almost at all, okay? At some of this region, actually because the momentum is smaller than 1 over r, we find out that the derivative is actually massively affected. Conversely, if the momentum of the axion is big enough, then who cares about the fact that there's an Earth here, right? I'm already having a very high momentum, so even if I make some changes at the scale of 1 over r, they're not actually going to significantly affect my derivative. Okay? So throughout this region, we can quite robustly show that the axion gradient is enhanced. Okay? And this is important because some experiments, this is indeed what they are sensitive to. Now, I mentioned this a bit before, but I do want to emphasize it specifically here. There is a region where the axion field gets attacked here. Okay? Basically, it is more worthwhile for the axion to kind of run away to minus infinity inside the Earth, because this line is when delta m squared is bigger than m squared. Okay? So kind of inside the Earth we are tachyonic. And in this region, our calculation is just wrong. Okay? So you should not rely on anything I'm saying if you're inside this region. It's just requiring a full UV model for the axion. For example, you can write down the full cosine potential, and then you would just move to the maximum of the field inside the Earth, the minimum of the field outside the Earth. We didn't do that. We just wrote the a squared term, and as long as you're outside this region, this should be sufficient. Okay? So in this region, we have a breaking of our effective field theory. Now, so this is kind of the 3 primary things we can actually reasonably talk about. However, as you will see, there's a lot of very, very complicated math going on here, and we cannot actually fully characterize numerically everything that's going on, even in here. Okay, we could only sample stuff and extrapolate. Okay, and this line, what this line is meant to do, is show you what perturbation theory tells us. So instead of trying to actually analytically solve for everything, again, because the math kind of is extremely sensitive to small numerical errors, instead of doing this whole thing, we just wrote down the original equation of motion, solved the 0th order equation, checked what is the next order correction. Okay? And the answer is that when you are along this line, the next order correction is roughly equal to the 0th order correction. So you roughly would expect order 1 modifications of the fields along this line. As you see, right, this line seems to extend beyond where I told you a moment ago things are affected. Okay? And the thing is, when you actually try to calculate things that are going, let's say, somewhere around over here, again, you just cannot numerically do this. What we could do to try to see whether this is actually, where things are affected, was look at whether the field amplitude is changed or actually its phase. And it seems like along this line, you're not actually making a to a over 2, you're making a to a times e to the I pi over 3. Right? So this is not a thing that you would actually necessarily be sensitive to in any experiment, right? Like who cares if you change the phase of the axion here versus the other side of the Earth, right? It's not really going to enhance or reduce your sensitivity unless you're trying to correlate experiments here and there, okay? However, this is more to help us understand whether it is justified to extrapolate from kind of roughly this region, where we can actually calculate things, to this whole part, and to say that we are not actually sure whether there are no effects in this pizza slice between the blue and the dashed line. Okay? So this is something that requires a more complicated calculation, and we'll kind of talk about later why we didn't actually try to do this. Now, it is important, I think, to show these are the actual, QCD axion in the usual sense of like the mass is related to the coupling constant. Okay? So this is this yellow band. Okay? And as you can see, basically it doesn't overlap with any of these colorful regions, but it does seem at around the milli-eV region to overlap with this line. So it could be that there is an effect for the QCD axion, however, it seems like the big effects are not there. Okay, so I think it's important to emphasize this. And if all you care about is quote-unquote the QCD axion, despite the original answer when you ignore the momentum, it seems like probably it's not too affected, but maybe there are some order 1 changes at the milli-eV range, which are going to require more careful work of things, and I will talk about this at the end. So, this was kind of the main plot, but let's try to actually understand why are these things correct. So, these solutions are going to depend on like weird Bessel functions, and just doing a Fourier transform, it turns out that as you go to higher and higher L mode, you depend on higher power on like this k times r. Okay? And this tells you that, if kr is very small, actually, I don't care about high L modes. I can just look at the monopole and the dipole. And this is just the actual, full solution for the monopole at the radius of the Earth, just to kind of show you what it looks like. And to show you that, indeed, we can kind of already see how the divergences are going to disappear, right? Because earlier, if I ignore the momentum, okay, so this k goes to 0, the cotangent can meet 0, and then this thing diverges. But as soon as I have now a finite momentum, okay, this thing plus that thing is never 0. There's always a finite, they are off phase from each other, so you actually cannot ever see actual 0. Okay? Now, another curious thing is, despite when you take the momentum to 0, it seems like the whole thing diverges. If I treat this cotangent as some order 1 parameter, and I increase delta mr, okay, increase the strength of the coupling, then on average this thing is just going to be 1 over delta mr, right? QR was square root delta m squared plus k squared, okay? So this thing is actually going to become smaller and smaller despite quote-unquote seeing these divergences, okay? So there's no more divergences, but there are still resonances, right? So whenever this thing is going to be 0, okay, this QR is going to disappear, so whenever the cotangent is 0, and we're just going to get 1 over kr, which if k is small enough can be a very big number suddenly. But outside of those, once we ignore these specific points where this thing is divergent, we're actually going to see that this thing is always smaller. Okay? So basically, again, if we're just evaluating things, it looks like this thing is just going to be scaling like 1 over the strength of the coupling times r. So what earlier, this delta mr. As you increase the momentum, the properties are a bit different. Again, the details here are not super crucial. And we also write it for the gradient, and opposed to the field value, the gradient actually seems to generically be increasing. Okay, basically, in particular, there's a large region where the gradient just becomes 1 over r, because who cares about the axial momentum when, again, there's a new scale, which is the radius of the Earth, so it's just going to be 1 over the radius of the Earth times the field value, okay, instead of being k times a naught, okay, so that's like, it can be a pretty hefty enhancement, and all of these are kind of the generic answer we are getting. And again, we also increased KR to try to see how strong they hold, and we need to find some level of reliability to these things, but again, there's only some level of extrapolation we can make before things are just, of actual numerical calculation we can make before the numerics just break down. They just become too strong. And the big issue, the main reason why they break down is these resonances. Okay, so what are these resonances? Well, basically, it seems, I will explain it in a second, but there are particular choices of momenta and like coupling to the Earth or momenta inside, where suddenly there's a huge increase of a particular multiple. So, you slightly change the momentum and there's nothing, and then bam, suddenly blows up. Now, there's a couple of ways to understand it. First of all, just in terms of pure math, just if you're wondering, like, how do you see this? Well, we have these spherical Bessel functions, but there's actually two kinds of them. Okay, and one of them wants, quote unquote, to be very big. One of them wants to be very small whenever you are in this kind of regime, where kind of for these guys, you are below where you should get a contribution. For these guys, you're above it. And you get the particular matching of the derivative and the function kind of chooses that you explode, okay? The math details are not important, but what is important is we do have a way to understand this also in terms of physics, okay? But I just didn't want to kind of just explain the physics without, saying like, oh, we could have guessed it we just guessed it to never check. There is kind of a mathematical way to understand it, but more importantly, there's also a physics way. So to understand why the physics tells that there are resonances, first, let's simplify things and assume there's one axion. So I'm sending a single axion, I'm asking what's going to happen whenever it meets the Earth. Well, it's coming from infinity, it's going to meet the Earth. Now, it's going to scatter from the Earth, so some part of it is going to get reflected and pushed, right back to where it came from, and some of it is going to transfer inside. The part that's transferring inside is going to reflect back and forth until at some point it leaves. Okay, so it's just going to run around, reflection, 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 until it leaves. Obviously, this is a simplified picture, right? Like, don't take this description too seriously. What is important is, again, we have this part of the axion that can reflect back and forth inside the Earth. Now, imagine that I'm not sending a single axion. I have a bath of dark matter that can keep sending axions all the time. So, the axions are coming from infinity with some momentum. But now, initially, some of it is transferred. But as I keep putting more and more axions, the part that is transferred is reflecting back and forth, back and forth. And because it's there for a very long time, I'm effectively getting an enhancement. So the steady state solution is one where these axions can actually be enhanced, okay, because of this repeated reflection. Now, this is only happening for very specific momenta that you get this very efficient reflection back and forth. And this is what allows you to actually very strongly accumulate. Now, only if you have k equals 0 can you get really perfect reflection, because otherwise you kind of have a preferred direction, okay, while this is a sphere, so it kind of makes sense that you wouldn't get perfect matching. But if the momentum is 0, then basically this problem is spherically symmetric, and also the boundary condition is spherically symmetric, so you keep pumping on more and more waves that can basically be reflected infinite amount of times. So you do get this essentially arbitrarily large enhancement if you assume that you had infinite time to accumulate these axions. Okay? But as long as the momentum is finite, this thing is finite. So, another way to understand the threshold, which is very different from this one, okay, is through the Schrodinger equation. So even though this problem is completely classical, okay, these waves have a large occupation number, the equations are the equations of motion with no quantum fluctuations and stuff like this, it actually is kind of a dual thing to the Schrodinger equation. Okay, what do I mean by that? Well, it's not really, duality in the sense that, you can really transfer from one to the other, but once you've assumed a specific energy, then these are your equations of motion, and you can kind of redefine the effective potential to be this, you can redefine the effective energy to be this, okay? And you just get a Schrodinger equation, okay? So by just kind of playing around with the time-independent parts of things, we can actually recover the time-independent Schrodinger equation. And the reason why this is a useful thing to do is that we actually, know that Schrodinger equations has bound states, right? Like, this is a thing we like about quantum mechanics. So even though it's classical, there are bound states here. And the step function potential, which is essentially what this thing is, has more and more bound states the deeper the potential is, okay? And basically, the first one appears exactly when Bauer saw the first divergence, okay? And indeed, you can associate immediately the appearance of these divergences with the appearance of bound states that have zero binding energy. Okay, as you increase the depth of the potential, all of the bound states become have a bigger and bigger binding energy. Okay, and every once in a while a new one appears. So whenever the binding energy, whenever you have a new state with zero binding energy, you can basically transition to it for free, right? Because your energy matches the energy of this bound state. Okay, so this is why kind of you can get this effective enhancement, because you have this resonance with another state that is basically of the same energy as you. Now, there's a bit of a subtlety here, because we do see this also when you have finite momentum, and then there are no, you cannot actually transition to a bound state because you have positive energy. Okay, so this is a bit of a subtle point, but it's still, in terms of the 2D spectrum of the problem, it turns out that it does match very close to when the problem has a bound state with imaginary energy that is very close to kind of the real axis. So the imaginary energy is kind of very small. Okay, so it's kind of still kind of correct even at finite momentum, but for zero momentum you really kind of see the divergence whenever there's a new state that's appearing with zero binding energy. Now, there's a couple of interesting features to these resonances. First of all, I already mentioned again, the first one appears basically when the momentum inside matches pi over 2. You can kind of do one winding inside the Earth. As we increase the strength of the coupling, actually the density of these states is going to increase as well. Okay, so if I have a very strong coupling, let's say this delta MR is like 100, then when I change it by 1 over 100, I'm going to see another state. If it's 1,000 and I change it by 1 over 1,000, I'm going to see another state. So the density of these states is increasing more and more for as long as these K are small, otherwise it's a bit more complicated. Now, as you go to higher and higher L modes, the height of these resonances increases. Okay, so it's still finite, but it's going to increase. But also the width decreases. Okay, so they become narrower and narrower, but also taller and taller. The dependence in terms of the parameter is actually super exponential. So at L equals 1,000, I believe it's like 1,000 to 1,000. Like it's not e to 1,000. It's like the height of this thing is 1,000 to 1,000 times what you would expect from, the standard no Earth solution. Okay, so these things are crazy high and crazy narrow. Now, we kind of talked about things as if the axion has a single well-defined momentum. This is not what actually happens, right? Like we have some virial velocity distribution for the axions. They spread around a bunch of velocities. So, if you really wanted to calculate observables, it's not exactly this, but roughly what you need to do is the two-point function of set observable multiplied by the axion distribution, okay? And it turns out that when you do it like with an integral instead of assuming a monochromatic wave, this will remove the super exponential behavior, okay? Because the width is again decreasing while the height is increasing, so the observable are actually not looking super exponential, but they can still be important, okay? So like maybe it's not like 1,000 to 1,000, but you can still get a pretty large contribution from the resonances. Now, however, it turns out that if the momentum of the axion is small enough, okay, then because of kind of the density of these resonances and the fact that, again, the momentum distribution is basically of the order of its average value, you're just not really going to see any of these resonances. Even though the density is increasing, the fact is that the momentum is small enough that it's just very unlikely, unless you fine-tune this coupling constant, that you will see a resonance. So hopefully, at least, for the small momentum part of the story, we can ignore these resonances, though again, as I will talk, there is some limited warranty to that statement. Okay? But yeah, but that's just what the answer turns out to be. Okay, so these are kind of the properties. And I want to move on to talk to experimental implications, then I will talk about kind of how I see this thing moving forward. So just again to remind us, even though we're taking a perfect spherical Earth, constant density, we're still seeing that you have a bunch of these multiple stuff. You can get field values that are decreasing, gradients that are increasing. You get these very complicated resonance structures. But at least hopefully for small kr, a lot can be learned by ignoring these resonances and just seeing what happens to the zeroth order and the first order multiple. Okay, but yeah, this is kind of the basic part of things. But now let's try to understand. Okay, again asking the important question: why should we care? Right? Like, how does this affect experiments? Well, the easiest thing is gradient-based experiments because they are basically always in the regime that either things are enhanced or nothing happens. Okay, so it's a bit easier to make arguments. At least they probably are either improving or nothing. And I kind of talked about gradient-based experiments last time I was here, but this is usually kind of my bread and butter. Basically, we're coupling the gradient of the axion to the spin of some fermion. So we are using some spin-based sensor to try to look for the gradient of these fields. Now, luckily for us, the gradient is enhanced by many orders of magnitude. You will see in a second, just how many. And this further motivates these experiments. However, it's not immediately possible to just convert all results to new ones and multiply by some factor. And the reason is that the gradient is actually only increasing in the radial direction, kind of pointing where the Earth is changing things. And also, usually at low frequencies we get daily modulation because the Earth rotates, the field momentum is kind of in a specific direction, so you kind of always rotate, changing your angle with respect to it. But here, because it's always kind of leaving, outside the Earth, you actually don't get this daily modulation. So there's a bunch of assumptions made in these experiments that are no longer correct. So we can't really do a recasting. Okay, one would need to redo the experiment analysis and actually check the right answer. Okay, but we can get a rough estimate of the expected sensitivity, and that's this plot. So this is the Axion coupling to neutrons in particular. Okay. There is kind of a bit of a freedom between how strongly you couple to the spins versus how strongly you couple to these density effects, okay? Like there's an order 1 coupling, which we took to be 10 to maximize the coupling to spins here. And these are kind of, in grayed out region are the old constraints. This orange one is one of my own. And I guess okay, technically also the blue one, but never mind. The important thing is that basically, originally they are sitting here, and you can see that this guy is getting like 9 orders of magnitude enhancement, okay? And again, the reason is that the Earth is so gigantic, okay, that it can lead to such massive effects even for very small couplings. And sorry, Marcus, I now see that when I said 10 to the 15, it's actually 10 to the 13 GeV. And I was estimating before, off the top of my head, when the effect is important. Now, it is important to remember, again, this earthbound. So whenever we are in this region, this means that you cannot actually have these models with this strong coupling to matters, like with the A-squared coupling, okay? So in all of this region, if you have this A-squared coupling, you actually cannot do anything, okay? However, we are scratching a bit beyond this point, right? And hopefully, as we improve these experiments, we can actually start to improve things even further. There is this wide dwarf bound where whenever this effect happens in wide dwarf, if you assume you know the full theory, it seems like there are some bounds, but I think that, there's less of a stronghold over it. And again, like, it's not, I think, impossible that we can reach beyond this line in the future. And it's nice, again, like, especially at low frequencies, it tends to be very hard to have these experiments be very sensitive because noises tend to be very big. But because the enhancement is actually increasing as you go to the lower frequencies, we actually get a pretty huge improvement here at low frequencies. So I think it's kind of a nice result in that context. Okay, so we can get like a huge improvement for these kinds of searches.
Sorry, can you explain? I'm not getting the picture of how exactly. So the gradient that's being probed in these experiments is over some time scale and some distance scale.
Yeah.
So maybe just focusing on one of these lines, can you just kind of tell us what that is? So what is that time and distance scale that's relevant for that experiment?
So let's, for a second, talk about, let's say, this one.
Yeah, pick one.
Okay. So this is the potassium covalent emitter. So in all of them, the gradient scale is actually extremely small. So you're measuring the gradient over...
just the distance scale of the experiment, it's measuring the gradient over some distance scale and over some time scale.
So
a good way to say it?
So the spin's coupled to the local gradient, okay?
Right.
So you're averaging over the local gradient over some distance, which is very small, right? So you're not actually measuring point A field value minus point B field value. You're just measuring gradient at point A, right? And you're averaging over a very tiny region. So in all those, the scale of the experiment is like centimeters, okay? So it's a very small scale.
And then the gradient is changing in time. So are you sort of measuring the DC part of the gradient? Or
DAC.
You're measuring at what frequency?
So this would be roughly 1 hertz. So this would be when the experiment is measuring at 1 hertz.
So you're measuring the fact that, and you're saying that the Earth is changing that by 9 orders of magnitude.
So what really happens is, because the Earth has existed for billions of years, okay, basically the field has had time to relax to a new average field amplitude, right? If you just turned on the Earth right now, the Earth would not do anything, right? It takes some time. There was another paper that came out with us that showed the typical time scale, and it's way shorter than the Earth formation time. I don't remember the exact scaling, because again, that was not part of our calculation. We just look at the steady state solution. But basically, the Earth allows you to accumulate axion fields for a very long time, okay? So basically, what really happens is that as you accumulate further and further and further, you're actually going to change the field value. Now, for the gradient, I guess it is maybe a bit more complicated, because you're not actually changing necessarily the average value at the radius of the Earth, but you are changing it inside the Earth.
Well,
Okay.
so that was sort of part of my question, is because you're focusing on these gradient-based experiments.
Yeah.
From what you just said, it sounds like an experiment that would be sensitive to the average value of the axion field would also see a huge enhancement.
No, so imagine for a second that the field gradient is usually assumed to be k times, well, not imagine. Usually the field gradient is assumed to be k times a naught, where k is going to be 10 to the minus 3 ma, okay? So this would mean that the field changes from order 1a naught to another order 1a naught number over the scale of the momentum, right? A scale determined by the momentum. But now, because of the Earth, sorry, so I was being a bit imprecise earlier, because this is a gradient experiment. I was describing what would happen on the resonance. But now what really happens is, that if the field, let's say, changed from 0 to a naught, from the center of the Earth to this point in Earth, the gradient would now be typically a naught over r, right? Rather than being k times a naught.
So, I mean, what I'm just getting at is just something very simple. Like, if I just make a cartoon of this thing as a sine wave, you can't, if you want to say that you're increasing the sort of average gradient without increasing the amplitude, then you're doing a huge effect on the, on the frequency or the wavelength.
Yes.
On the other hand, if you're just scaling everything up, then you're scaling. So I'm asking sort of,
but
what is the cartoon of this? If I drew the standard thing as some sine wave like this, now I want you to draw something that has 9 orders of magnitude larger momentum, but it does have or it doesn't have 9 orders of magnitude or whatever, larger amplitude.
So the thing is, because in the Earth there's a different momentum, okay, just locally.
Is it possible to draw the picture or not?
Yeah, I mean, we have actual plots in the paper.
I mean, just a cartoon.
So the cartoon, again, the simplified picture is, imagine the following.
It's really just missing something basic.
Let's say this is the Earth. So this is kind of A.
Well, I'm asking for the spatial distribution of the axion field.
So this is the center of the Earth. This is the edge of the Earth. This is the field amplitude. Let's say it looks like this.
But over your experiment, not over the Earth. I mean, and inside your experiment, over that 1 centimeter size inside your experiment, what is a cartoon, what does the dark matter distribution look like if I neglect the Earth and I keep the Earth? And
So
how
my
does it change?
experiment is far smaller than 1 over the radius of the Earth.
Yes, I understand that.
So over the scale of my experiment, the axion field is basically not changing, right? Both the
No,
first...
but I mean, I'm comparing the case where you include the effects that you're talking about compared to the case when you don't include those effects. Over the 1 centimeter, how is the axion field different?
Let's say this is the 1 centimeter squared of my experiment. This would be the axion field value along it for ignoring the Earth. This would be the axion field value along it if I don't ignore the Earth. It's like a little slope. The slope is of the order of 1 over r Earth. Because my experiment is much smaller than the Earth, this would be a change at the scale of
And
like...
it's because the original, I'm sorry, so I think the thing that I was missing is that the idea, the original slope was so small that even if it changed it a little bit, that's significant compared to, you know,
Yeah, exactly.
that's the idea.
Yeah.
Okay, I'm sorry, thank you, I
Great.
didn't understand that.
Great. Cool. So Axion photon experiments are more complicated because the equations of motions are this. So I have some background magnetic field, background electric field. Usually it's just a background magnetic field, but there are exceptions which we talk about. And you produce some new electric field, new magnetic fields because of these things in the presence of axions, okay? And the thing is, usually you just drop the derivative of the axion field because you say, okay, the axion is not relativistic, so who cares? But because we have this enhancement of the gradient and suppression of the field value, you cannot necessarily do this, okay? And if you work in the magnetic quasi-static limit, which is basically think ultralight dark matter like what DM radio is looking for, not like what ADMX is looking for, so Axion that has a Compton wavelength, which is far bigger than the size of your experiment, okay? So very, very light stuff, so yeah, DM radio shaft. Turns out that the contribution of our modification would actually be introducing a new contribution to the electric field. So usually we put a magnetometer, we try to measure the magnetic field, but it turns out that this would also produce an electric field, which can be quite important, okay? Now, depending on the exact details of the experiments, again, things can be very different. And just like you saw before, a lot of the region where the strongest effects are happening is kind of in contention with some astrophysical bounds. But it is going to be much harder to just convert old results to new results, because here there really is kind of a very complicated new equation, and one needs to be more careful, and we just pointed out and did some rough estimates for when it would be worth it to maybe look for electric fields, when it would be worth it to look for magnetic fields, and how different experiments are going to be affected. But it is a much more complicated story. Now, there are other experiments that one can talk about. For example, long-range forces, but also atomic clocks, time-dependent EDM. Basically, each of them needs its own kind of dedicated work to see what is exactly the configuration of field derivatives that it is sensitive to. We didn't really do that calculation, we just kind of drew the parameter space just so we have it, to kind of see where the effects are going to be important compared to the usual plot people put. And we do see that most of these experiments are kind of at the ultralight regime, where actually the EFT breaks down, so it is questionable whether you can think of these experiments as sensitive to something that has a reduced mass, like an axion-like particle, okay, so like something with a negative mass inside the Earth compared to a positive mass, so the negative mass doesn't really seem to work. The gradient seems to be enhanced for some of those. We didn't really do the full calculation. Again, this would require a more careful work, but it does seem like, they usually are not in the region where the field value is suppressed. They are more likely to be in the region where the gradient is enhanced. Whether or not this matters depends on the experiment, and we just kind of did the drawing to show how the different experiments look like on top of this plot. Now, future directions. So I think one of the reasons why I keep saying, oh, we didn't do this, is that as soon as you see something super exponential, you already know you're doing something that's not actually nature. And the reason is I am more than a super exponential correction to the Earth's mass, right? Like me standing here, right, is more of a 1,000 to 1,000 correction, right? 1,000 to the minus 1,000 correction to the mass of the Earth, right? Like the Earth is not a perfect sphere to the super exponential level, which immediately tells you that any observable that is sensitive to super exponential corrections is not well described by your toy model, okay? So we need to find a way to actually treat this, right? Like what actually happens. Now, my guess, which is based on physics intuition, but not necessarily is correct, is that what would happen is that the resonances are going to be wider, okay? So it's not obvious whether once you integrate over the resonance width, you would actually get the same total contribution, or whether there's going to be a Q factor suppression or something, right? We don't actually know. But my guess is that it's definitely going to be wider and less high, okay? And how much this affects things, again, we need to come up with a way of actually treating the fact that the Earth is not a perfect sphere. My best current idea would be to try to do perturbation theory, where we kind of treat our original solution as a zeroth order answer, and then on top of that, add basically something that's like a random function that has like zero average, but has a finite 2-point function, right? Has self-correlation, but not zeroth order integrals, first order integrals, and maybe we'll be able to see kind of how adding something that's like random corrects these things. But of course, again, the Earth is also oblate, right? Has oblateness. I'm not sure how to say this, but like is not a perfect sphere to I think the level of like 0.1% or something, right? And that's not just a random thing, right? It has structure. So this will only account for some of the story, and it's not obvious how and whether it's even possible to really try to get a better picture of a more realistic model of the Earth. Another future direction I think is interesting is can we actually populate these bound states, right? All this time was doing essentially elastic scatterings. The axions are coming in, they're not changing the energy. However, because we actually do have this bound state spectrum, it is interesting to think whether if you now allow inelastic scattering or even production, you can actually have particles sitting inside of these bound states and essentially have like a Bose-enhanced bound state, right? To keep on pumping more and more particles there, and this would kind of give you new field values to be sensitive to, okay? Another interesting direction is, are there other terrestrial objects where this would be interesting? So, Sun, Jupiter, to be clear actually, because we are super, exponentially sensitive to stuff, probably they are even important for, our calculation on Earth is probably actually affected by the fact that you no longer have these very narrow resonances because there's another object over there that has its own structure, right? So like, strictly speaking, this is also a part of the imperfect Earth. But maybe a more interesting question is, for example, neutron stars, it turns out here we're not sensitive to for the QCD Axion line. However, for neutron stars, it turns out that the lines actually do overlap. Okay, this is actually affecting how neutron stars, the profile of Axion dark matter in neutron stars, it seems like. We didn't do the full calculation. And I only know a single observable that actually cares about Axion dark matter profiles around a neutron star, which is you can try to convert axions to photons in the magnetosphere of a neutron star. That's the only thing I know that cares about this. But maybe if we now see that there is a bigger enhancement, and again, this would require a dedicated calculation because neutron stars also have gravitational effects that are, order 1 changing the velocity distribution, right? So there are more complicated calculations than what we did. You cannot ignore gravity there. But it is interesting, for example, if you now enhance the Axion gradient or Axion field value by a factor of 1,000 there, who knows, maybe now there are observables that we would be sensitive to, right? So that's another future direction. There's a lot of other stuff that we kind of are thinking about. None of this, we have spent enough time to really say, oh, there's something clearly working there. But for example, we also looked at the profile of the field as a function of distance from the Earth and also underground. Turns out that quite generically, even though the field we look for, that's 1,000 kilometers underground, but maybe we can be indirectly sensitive to if the Axion field profile is suddenly enhanced by 10 orders of magnitude inside the Earth. I don't know. Again, we haven't really came up with anything that would work. It's also interesting to think other BSM models where the mass is modified and suppressed inside the Earth that would also give you similar phenomenology. Or even for axions, we were very much like whether or not we overlap with the QCD axion or blah 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 was very much related to the fact that the axions are virially distributed. However, if you have axions that, for example, are very cold, have streams or some other models which suppress the velocity distribution, you could actually get, the slicing of the parameter space would look different. Okay, and in particular, again, basically the colder they are, the more centered they are around kind of the Earth's rest frame, the bigger the effects are going to be. Okay, so it could be that for such models, again, there are bigger effects that are worth thinking about more carefully now. And with this, I think, let me just summarize. Sorry, yeah, a bit over time. Basically, the modifying of the axion mass inside the Earth can lead to very complex and rich phenomenology. We should not forget about the momentum because it does, allow us to be somewhat safe for pretty large swaths of the QCD axion parameter space that are otherwise under suspicion. This is really just a step forward, right? Like, again, this is in some sense a toy model. There's so much more to really explore here to be able to make more robust statements, and I think also to really see the full phenomenology of these kinds of models. And yeah, thank you very much for listening.
Questions?
So for detecting the gradient of axion field, I think they also need to take into the coherent time into account, because the way you trap this axion is like from the beginning of the existence of the Earth. So I suspect this axion, even though they are trapped, they will be kind of messy. So the coherence of this axion may be bad.
So the thing is, if we're ignoring the resonances, which is where we see like the major enhancements. So the major enhancements are not from the resonances. For the resonances, like I had a whole analytic calculation that shows the individual contributions. Until at some point I realized, okay, like again, the Earth is not perfectly spherical to this level. So even if I did, get the estimate from our toy model, it's just meaningless. But if we ignore the resonances, this is where we get the enhancement. And within this regime, there's not actually much of a change in the coherence time. The work of the other people that came out at the same time as us that also looked at deformation a bit more, did a more accurate estimate of the coherence time, but it's only changing by order 1, because it's not like there's a huge difference between the momentum and the momentum divided by by 1.5 or something, right? You still have the same momentum distribution, it's just that the gradient is now enhanced for each of these k modes. So it is modified a bit, but the coherence time is not too different. This is important for all of the different experiments. For the resonances, it's really crucial. Again, like our model is not realistic there, I want to emphasize, but for the resonances, a feature of them is even if the integral is finite, essentially the coherence time is like infinite. Okay, if you assume the Earth is perfectly spherical, though again, probably it's 10 to the minus 3 perfectly spherical, who knows what the width of this will induce. But basically, what this means is that, if you could use this toy model, you would actually get that the axion coherence time is actually massively enhanced for particular frequencies. Usually we think of it as just one giant distribution, but it's just no longer a single peak, it's a bunch of peaks, so you need to be a bit more careful. But if we're treating like the standard story of like where we see the massive enhancement for the gradients, the changes in the coherence time are not significant. They're not, the dependence on like order 1 changes to the momentum is actually very minor, because the actual gradient is modified from being momentum times A to just being A divided by R. So actually, in some sense, you are less dependent on the momentum distribution than usual even. Okay, usually you're linear in the momentum. Here you're actually you have zeroth order dependence on the momentum, the external momentum. Okay, so there's even less of dependence on the momentum than usual, but we already know that that's not a major change in coherence time, because that's basically the regime that usually you work with in like the axial photon couplings. So usually for them, they don't care about momentum, and we know that the coherence time is roughly the same thing for these kinds of, for the magnetic quasi-static limit experiments compared to gradient coupled experiments. So again, there is an effect, and the other group did a bit more careful looking into it, but it's not, it's like an order 1 change in the coherence time.
Okay. And for your case, you don't have to care about the temperature of the Earth. Is it because if they are thermalized, they will just fly away anyway? So you look at a regime which is trapped but non-thermalized regime?
So we are in a regime where basically the trapping potential is, so when the effects are very big, the trapping potential is extremely deep, and it doesn't really care that much about the density, the time dependency of like the particles moving around in the Earth, because you are doing this elastic scattering, so you're not actually depositing energy inside these particles. Now, it is certainly correct that this would lead to some correction, just like again the fact that there are inelastic scatterings would lead to some correction. We did not account for this, but the thing is that for basically all the parameter space where this effect is important, your correction kind of to the momentum has to be much, much bigger than the velocity of the particles in the Earth. So you wouldn't expect them to actually do much. Okay?
Because your case, the trapping happens at the boundary between Earth and space.
It's just because for this effect to be important, you just need the change in the momentum of the axion to be so big inside the Earth. They are much faster, basically. Faster maybe loses a bit of its meaning when you change the mass of the particle as well. But it's more about the fact that like the momentum of the Earth is not really super crucial for the scattering process. We're not really depositing momentum there, right? So you can not deposit momentum in a particle that's moving around or not moving around. It's not really changing the kinematics that much, right? Like the important thing is that there's an average number density of these particles here. Again, in principle, also the fact that the Earth is not a continuum of particles, but like has a finite, right? Like would also change things, but that's also something that's relevant for like pions and stuff. So you would also see that for their change in the finite density potential. So because it's not super relevant there, I mean, I guess.
So are you saying the thermal velocity of the axion is just small compared to the momentum that you?
I mean, yeah, sorry, of the Earth, like, right, the thermal velocity of the Earth particles is just very small compared to what you should care about for these.
So it's because you're effectively interacting with so many Earth particles that the mean velocity is small.
I was just thinking about the fact that the individual velocity, but I guess you're right that that's also important because indeed you are actually seeing a coherent effect. So that's further suppressing. I wasn't thinking of this, but you're right as well. I mean, the thing is that I suspect, for example, the fact that the Earth is non-uniformly dense is a much bigger effect because there are order 1 changes in the density of the Earth along its axis. And that's a much bigger effect than the fact that instead of having point-like little spheres, actually things are changing. I mean, I guess what you're saying is also true for like the chiral Lagrangian, which is what we're using to get the answer for what is the modification of the potential. And I guess there we also know that until you reach like QCT temperatures, things are not that different. No, but yeah, I guess it is a bit different because here we are talking about changes over a long time, right? We're not talking about like a point-like interaction, so the argument doesn't really hold that much. But again, to me, it's more the fact that I cannot tell you that there is no effect associated with this. I can tell you that there are bigger issues with the toy model than this.
You're silent? Okay, let's thank Itay again.
Yep.